everyone to another session of the Redditorium seminar. We are joined by Professor Ambar Sengupta and his PhD student Dion Mann from University of Connecticut. They will be speaking about diffeology, a gentle introduction. So yeah, start. Floor is yours.
Thank you. Thank you, Irfan, for inviting us, and thank you all for being here. So the title is Diffeology, a Gentle Introduction. I have to apologize. I don't know how gentle it is. I think the first version I wrote of the slides, I looked at them and then I thought, okay, this is not gentle. So I tried to, make it a little more pleasant, but we'll see. So this is just a quick look ahead. We'll look at the background of the subject and how it applies to the relationship to spaces of functions. And then we'll go through some slides for where we look at the actual definition of diffeology, and then some properties that are category-theoretic. Diffeology is a kind of a geometric theory. So the notions of tangent spaces and differential forms are useful or necessary to some degree. We'll look at those and then some notion of integration, and we'll conclude with a look at some possible definitions. The subject is not advanced and not definite. The definitions are still evolving. I'd say the definition of diffeology is fixed, but beyond that, many things are still fluid. So the overall goal is to do calculus, mainly differential calculus, on quite general spaces. And what do I mean by general spaces? So we know traditional calculus is done on R or Rn, and then beyond that on manifolds. And diffeology theory takes it beyond manifolds. And we'll see why that is necessary, or why that could be useful. So the background, one can trace back a set of ideas very far, but I kind of took it back to 1966, which isn't that far back in relation to my lifetime. So J.W. Smith, he defined a structure on a set X with which one could do calculus. And so it was by saying, okay, these are a set of functions, and we will take these to be the smooth functions. So it's not that there's a definition of smooth function. You just say, here's a bunch of functions, and we'll call them smooth, and here are properties that it should satisfy. I don't know, like the sum of two smooth functions is smooth. A composition of a smooth function with another smooth function should be smooth, things like that. So that's where J.W. Smith started. Then Sikorsky developed that idea further. Now, Oleg Viro is really a low-dimensional topologist. And I know of this paper from 2007, which is not at all mentioned in the general literature. And the only reason I know of it is because in 2007, I was at LSU, and Oleg Viro came to give a talk in topology, but he said he wanted to give a second talk on calculus on sets, something like that. And he clearly valued it and enjoyed that subject very much. I don't know if Viro looked back at Smith's work or anything, but he presented some quite intriguing ideas. And unrelated to diffeology, I also remember he talked about finite topological spaces. And you might say, well, how interesting can they be? It's just 5 points. But he showed within minutes there are interesting questions you can ask about such spaces. Anyway, so that is that track. Then there's a whole series of papers by Katie Chen. Now, Chen's objectives were related to homotopy theory, so about loops on spaces. And to study them, he invented this notion of iterated integrals. Well, iterated integrals, you can say, well, what's there to invent? You just keep integrating, and that is true. But in this context, it is a very intriguing theory, a structure that has been used on and off in various different things, but that is also a subject that is strangely not quite mainstream, although there is no reason why it shouldn't be mainstream. Now, in developing his theory of iterated integrals, he did integration along paths on some general spaces, and he called them differentiable spaces. So this is also a type of space on which one can do calculus, and he defined what they were. Then on a completely separate track, there is this work of Jean-Marie Souriau, who was studying dynamical systems, I think. And he had these ideas of generalized Lie groups. I have to say, I myself haven't looked at Souriau's work, at least in the last many years. My understanding is that he was looking more at Lie groups and groups of mappings. His student Donato did further develop these theories further, and his other student, Patrick Iglesias-Zemmour, actually, as far as I can tell, he's the first person to define diffeology. The idea yes, he was Souriau's student, and really the idea goes back to Souriau. But still, the fact is that it seems Iglesias-Zemmour was the one who officially defined diffeology. And then he has a book in 2013 that might be the last word on the subject at this point. It's a really comprehensive account of the subject. But again, let me say that the subject is still evolving. Many of the fundamental definitions are not quite settled. Of course, he has given some, some excellent definitions and much more importantly, many results. Ultimately, a definition's value is, based on the results you prove. Okay. So now let's look at function spaces. You look at all infinitely differentiable functions from some space Rm to Rn. This space of functions is infinite dimensional if you think of it as a vector space or in any sense. And there is no, I chose these words to be very careful, standard, useful, traditional manifold structure. You can always define a manifold structure, but there's no universally accepted structure of a manifold on this. There is a book by Mitchell, I'm not quite sure if that's how the name is said, who studies infinite dimensional manifolds from the traditional analysis standpoint. And he might have some differentiable structure on this, a manifold structure. But nonetheless, there's no widely used such structure. I've said Rm to Rn. You can also think of paths, like 0, 1 to a manifold M, manifold meaning Rn some space, or loops. The C infinity S1M refers to loops on a space M. Okay. These are interesting spaces, but they don't have this manifold structure, and therefore there is no mathematical machinery that can be used on them. And yet these spaces appear certainly in theoretical physics, where physicists have kind of ad hoc methods of doing calculus on them. Physicists have been doing calculus on function spaces for many decades, but they just do it as needed. They'll develop a definition of derivative, or they won't define it, but they'll use it anyway. Okay, so now we step closer to what a diffeology is. So we take a set X, okay, and we take a parametrization of this set. I don't mean the entire set. What I'm saying is that you take some like coordinates T1, T2, Tn, and for this point where T1, T2, Tn runs over some subset of Rn, some open subset of Rn. It could be all of Rn. And you associate to it a point psi of T1, T2, Tn. So we could think of T1, T2, Tn as coordinates of the point, but it's not a very, it's a very rough viewpoint. Because look, I don't even require that psi be 1-to-1. It could even be a constant map, right? This would be very strange to think of T1, T2, Tn as coordinates if the whole map is a constant. But nonetheless,
do you require Rn to be fixed, or do you change the n
no,
also?
that is a great point. Rn can be any n, and that open subset U can be any open subset of Rn. Of course, many open subsets, if you take an open ball in Rn here, if you take another open ball in Rn, same Rn, there is a smooth mapping back and forth between them. So changing the open set, not that big a deal, but changing parameterization is a big deal. So in particular, you could take R to the 0, which I consider to be a 1-point space. And this would be one of the things we use. And these mappings are called plots. So that's the key notion in diffeology. We'll start now. Here's the official definition, which goes back to Iglesias-Zemmour's thesis, I believe. So a diffeology D on a set X is a collection of maps from U to X. U ranges over all, sorry, there is a gap between all and non-empty. All non-empty open subsets of all Euclidean spaces. By Euclidean space, I mean Rn. Okay, and these are called plots. They're required to satisfy some properties, which are pretty natural. So if you take a plot psi and you kind of pre-change the coordinates by doing a transformation theta, T1, T2, Tn, then what you get should be also a plot. So for example, on the real line R, if I use T, the usual point, I don't know, variable T as the coordinate, then this is saying T square is also a plot. T cube is a plot, sine T is a plot. Any C infinity function of T is also a plot. So in that way, you can see it's a very general class. This one says that if you have a function on some open set such that locally around each point there's a name. So I'm using this term. Okay, so let me just read it. So you have an open set U in Rn with the property that around each point there is a neighborhood Ui such that this mapping psi, when restricted to that neighborhood, is one of our plots. Then the whole thing we will take to be a plot. We should think of plots as C infinity functions. So certainly if a function is C infinity in a neighborhood of each point, it should be C infinity. By C infinity, I mean infinitely differentiable functions. Let me write the third one and then we can pause for some questions or comments. So the last one is saying that any constant mapping is a plot. So this is, again, you see, is very different from actually a coordinate system. This really is giving you a notion of smooth functions into the space. So again, a diffeology is a bunch of functions into our space X with three properties that are natural. And we will think of these functions as being smooth functions, infinitely differentiable. Of course, there is no notion yet of infinitely differential, but we will think of them that way. Any questions? So again, a diffeology is a bunch of functions into the set X from various open sets with some reasonable properties. Yes.
So given an open set, can there be multiple plots
Yes.
from that open set? Okay.
Certainly, yes. I mean, you could take a constant function, any constant
Oh
function.
yeah, okay, yeah, every constant.
Yeah.
Okay, yeah,
But
that's
it's
true.
good
Okay.
to probe this definition. I have come back repeatedly to it and wondered, is this also a plot? But that's right. That's because, yeah, I mean, just your question shows that it's, yeah, it's a huge collection, really.
This is Matt Ensall in Rolla.
Yes.
I have a question
Mm-hmm.
for you. The way it's written here, it says it ranges over all non-empty subsets of Euclidean spaces.
Correct.
I actually have two questions. First, if you mean all of them, at some point you said something you said suggested to me that some of them would be enough, in some sense, to be a diffeology.
Okay.
But if you mean all of them every time, then why not include the empty set? That's the other question. So
no, I was that's another example of probing this definition. I confess that it was only last night when I was preparing the slides. I said I wrote non-empty. What's wrong with an empty set? So what is a mapping from an empty set to a set? I think any such mapping itself is empty. Is that right? I find these things.
That is correct. That is correct.
Yes. It could be used, I think.
Well, that's a minor concern.
No,
the bigger
it's logical. As I said, I also thought, but I didn't get very far on thinking where that would lead to. But perhaps we could just say all open subsets.
And then you mean all of the open subsets of all Euclidean spaces?
Correct.
Then?
Yes.
So it's a category. A diffeology is a category. It's not or it's a proper class. It's not a set.
So we are going to take by all Euclidean spaces, I mean all Rn, where n ranges over 0, 1, 2, 3, and so on. So I think in that case, it is a set, isn't it?
Oh, okay. Yeah.
Yes. But if
so you're only taking finite dimensional spaces.
Yeah. Yes, that's right. And
I think Euclidean usually means finite dimension, doesn't it?
well, it's up to the definer. But you could, I think there could be some other definition of Euclidean space that is not Rn specifically, but something that's sort of isomorphic to Rn. And then we might be off into non-set territory.
Well, that's true. So if you can have, in this case, I guess you would have a proper class, but you can reduce it by equivalence under isomorphism to a set of representatives.
Yes.
Yeah.
Okay, so that's
Thank you.
sure, that is a diffeological space, and I feel like just getting to this slide is, I think I've accomplished something, because that is really the new idea. So a diffeological space is a pair, the set X and the diffeology on it. Okay, this is just, by the way, I want to acknowledge something. Many things I have discussed with Dion over the last year or so, but many things I've also discussed with ChatGPT. And in particular, the first version of these slides was prepared by ChatGPT. I had to make some major adjustments. But, this kind of display, I don't think, to be honest, I could create this display. That was done by ChatGPT. I mean, the content I'm responsible for, but the display I give full credit to AI. So this is just a kind of a contrast. The manifolds have local coordinate systems. You give me a point on a manifold, I should have some coordinates associated with it, x1, x2, xn, polar coordinates, whatever. Plots, they go the other direction. You give me an open set, a plot is a smooth C-infinity mapping. That's how we think of it, from U to X. And this is, below it is just a bit of notation. Sometimes we want to focus a plot at a point P. Now, this is a bit awkward because for manifold, a chart can be around a point. You take a neighborhood of that point and you define a chart. But with a plot, we don't have a notion of around a point yet. So all we require is that we fix some base point, like the origin, use 0 and like a particular point P. Okay, so here's some examples. So two extreme examples. You have, I guess the smallest one on a set is all locally constant maps. What does it mean, locally constant? It's a mapping that is constant on each connected open set in every Euclidean space. I mean, if you take a bunch of disjoint open subsets of Rn, you could certainly take a function that is constant on each of them, but they are just different constants. And we do want them to be included in the diffeology. So that's one extreme where you are allowing only, basically forget about locally, it's just you are saying only constant maps are plots. Okay, this is obviously not going to be very useful. The other extreme is you say, okay, every map is a plot. All maps we declare to be C-infinity. This also is too wild, but nonetheless, this is to point out that the definition of diffeology is so weak in some sense that it permits these two very extreme things. So in that way, it's a bit like topology. Topology also is a very useful thing, but on a set, you could have discrete topology, indiscrete topology. Okay, if you are familiar with manifolds, then I want to mention that if you have a manifold M, then it has a standard diffeology on it, where the plots are, for a manifold, there is an established notion of smooth mapping, okay? And we just say, well, we are only going to take those smooth mappings as our plots. Then the diffeology is basically defined by means of the existing structure on the manifold. Okay, so you can also ignore this example. Next is the notion of subspace. I have a diffeological space X, and you give me a subset, okay? any subset, and we can construct a diffeology on it. What we will do is we will say that a mapping into this subset is a plot only if it is in the original collection of plots. It's just that its values lie within the subset, that's all. The definition is simple, but it leads to some strange things I don't always find comfortable with. So whatever, sometimes it's hard to absorb a definition on the fly. But the thing is that if you, yes, Irfan, did you have a question?
Yeah, I'm just thinking about what locally constant maps are. So I think you define them by saying that around every point in the domain, there is a neighborhood on which it is constant.
Correct.
But the maps themselves, maps of such kind themselves could be very wild, right?
Yeah, I mean, if you take...
It would be hard to check when a map is locally constant.
Yeah, so for example, let's take a subset of R that consists of two disjoint open intervals. The interval 0 to 1, the interval 5 to 7. If you take a function that has the constant value 15 on the first interval and the constant value 17 on the other, that is a locally constant map, but it's not constant.
But if I guess you did mention this, if your open set is connected, then it has to be constant. Okay, yes, okay, yeah, okay, now it makes sense. Yeah, I was thinking there might be wilder examples, but no, I understand.
No, that is. It's a bit like in calculus, we have, if the derivative is 0, then the function is constant, but it actually is constant on each connected open set, not constant everywhere. Okay, so there is a notion of subspace, whatever the definition may be. Then, unfortunately, this is not so gentle to understand this next point, but it is an important thing. I mean, you may just want to take away the following, that if you consider the set of all infinitely differentiable functions from m variables to n variables, this infinite dimensional space has a natural diffeological structure, it turns out. And, as we said, if you want to look at what it is you take an open set U and you say a mapping is in the plot if, as a function of the U variable and the Rm variable, it is C infinity. Again, as I said, I myself find it difficult to absorb a complicated definition on the fly. Sometimes you just take it as, okay, there is a definition and it's not super complicated. But I can answer any questions now or later about it. So the main point is that there is a natural diffeology on the spaces of functions, infinitely differentiable functions. So that is what makes this theory so useful. Now, okay, so we have diffeology. Then there is a question, so when is a mapping from one diffeological space to another smooth? By the way, in this theory, there is no notion of well, maybe I shouldn't go there. I was going to say there's no notion of like 3 times differentiable function or something. And I think there isn't. It seems the way the whole thing is set up, everything has to be infinitely differentiable or analogous to infinitely differentiable smooth. So a mapping f y to x is smooth if whenever you take a plot on y, so that psi u to y, and you compose it with f, what you get is a plot on x. And here's a commuting diagram. So in this triangular diagram, the vertical arrow u to y is a given C infinity, given plot on Y. And what we are saying is that, well, then if I compose the vertical down arrow with the diagonal up arrow F, what I should get should be smooth, right? Composition of smooth functions should be smooth. So F composed with psi should be a plot for X. And if that's the case, then we say F itself is smooth. No matter what plot you take and pre-compose it, the result should be a plot. So this gives us the set of all smooth mappings from one diffeological space to another. C infinity Y to X is the set of all smooth maps. And again, as before, the set of all smooth maps from one space to another turns out to have a natural diffeological structure. So again, this is what makes the theory of diffeology so useful or applicable, let me say. That this huge space of all smooth functions is itself in this category. In the special case where, if you are familiar with manifolds, in the special case where X and Y are manifolds, it turns out this definition of smoothness agrees with the traditional definition. So it's not like something new that doesn't agree with the established notion. Any question?
Ambar, I'd like to make a comment if that's okay.
Yeah.
So I think this definition of smoothness, you had mentioned this earlier, but to me, this is one reason why diffeology seems more accessible than differential geometry. Because if you think about, the standard definition of being differentiable, you have that limit definition, right? Which is, it's a nice definition and one can work with it. But with this diffeological connection here, and in the case of manifolds, it's actually the same thing, it's equivalent. It seems a lot easier to work with because a lot of times what happens is you'll define plots based on some property. And so to check if a map between diffeological spaces is smooth or not, you just essentially have to know what the composition is, and then you just have to check if it has that property that makes it a plot. So to me, I find it makes diffeology a lot more accessible, as you kind of mentioned earlier.
Yes, thanks. That's right. We never actually have to take a limit or take the derivative, something like that. It reduces it to something more algebraic in some sense.
So I also have a question.
Yes.
If you go back to the previous slide,
Yeah.
is it clear what the plots are in this C infinity Y comma X space?
No, I won't say it's clear, but sorry, do you know where I had, do you see this at the
I
back?
see.
So you would have to replace Y and X here.
I see.
So let me put it this way. This psi u is a parametrized class of functions. You have a bunch of functions parametrized by a parameter u. So then you look at it as a function of both u and the point p, psi u p. And this is a function from, well, open subset of Euclidean space to Euclidean space. And you can say this is C infinity, smooth. Okay. Significant question again, that's right. So here's a funny thing, by the way, we're doing calculus, but I haven't mentioned any topology. And that is an amazing thing about diffeology. you can do diffeology theory without bringing in any topology on the space. And that is kind of disturbing. And this also reminds me of that talk I heard by Vero back in whenever it was, 2006 or something, where he stressed that you don't need a topology to do calculus. It sounds bizarre. But the fact is that you can construct a topology out of a diffeology. So what you do is you just say, well, okay, I've got a bunch of functions called plots. I'll require that they be all continuous. All plots must be continuous. And that gives you a topology. I think one has to say it's the largest topology for which all plots are continuous. But here is the statement that really its diffeology is smoothness. The central concept in diffeology is smoothness for functions. Topology is to Y is also a diffeological space. I've mentioned this before, but from a category-theoretic viewpoint, this is something also very nice. I mean, if you think of, two vector spaces, the set of all linear maps from one vector space to another, that is also a linear space. But if you take two groups and you look at all homomorphisms from one group to another, that is not naturally a group. So, but in some cases, or I don't know, two topological spaces, the space of all continuous maps from X to Y, you can give it a topology, but it's not in some standard way that it is itself a topological space. So it works for diffeological spaces. Okay, we don't need to look at this, but look at the thing at the bottom. It says, therefore, well, just a note that path spaces, which are also mapping spaces, right, are diffeological spaces. Okay, now in manifold theory, there's the notion of tangent space. You think of a surface and you think of a vector that is tangent to the surface at a point. This is a weakness of this theory of diffeology. There is no universally agreed upon notion of tangent space. I think even I did not find one in Iglesias-Zemmour's book. Dion, you might be more familiar with it.
Yeah, I don't think he talks about it in his book.
Yeah,
There
I
are
think he even
notions
says
outside.
somewhere that maybe it's too ambiguous or complicated to be worth studying, something like that. But I just want to say that there is a notion. In fact, there's more than one notion of tangent space, and they're not equivalent. That is a bit sad. But I personally have found this one notion, which is called internal tangent space, quite useful. And I don't want to go through the definition, it's a bit technical. But roughly speaking, if you are given a plot, meaning a parametrization, and then you have a vector originally, vi, then you can move it over to the space. Again, if you think of a parametrization, and it may be a very bad parametrization, but nonetheless some parametrization of a surface or X, then as you move along some direction in the original parameter space, you think of it as giving a tangent vector in X. So there is this notion psi I vi. And again, I won't spend time on it, just to accept that there is a useful notion that utilizes the parametrization. I mean, the bad thing is that if you take a plot that is a constant plot, then this is a kind of a strange thing to have. Anyway, so it's not as nice a notion as the tangent space for manifold, but I found it still quite useful.
So since you're
Yeah.
calling them vectors, you should be able to add them
Yeah.
together.
Yes, that is right. So if you are sticking with the same plot, then addition is just addition of the original vectors. The original vector meaning vi, that is on the parameter space. But your question is brings up the uncomfortable thing that I could have a vector v that has a representation in one plot, but it has no representation in some other plot. For example, if I take the constant plot, I can't get to, let's say from a one-point space, I simply cannot get to a non-zero vector. So I'm not able to add vectors that are coming from different plots. So some machinery is needed, and this, just take it as a picture. You can think of, it's possible to do this in a category-theoretic way. There is some diagram, and then this tangent space appears as a co-limit, whatever that means, okay? It's like a direct sum. Roughly speaking, it's a direct sum of all the various tangent spaces one can get. But some identifications are needed, etc. So next, so we did diffeology, we did diffeological space and its topology, and we looked very briefly at the tangent space. The dual of the tangent space are called forms, and spaces of forms are differential forms. So this also, again, this is a bit technical, I'm sorry. We say that little omega is a K form. You should think about it as like dx is a one form, dx dy is a two form, dx dy dz is a three form. So similarly, omega is some K form. So what it is saying is that if I take any plot, any parameterization, it should correspond to a form on the original parameterization space, parameter space U. And since you can go back and forth between different parameterizations using smooth maps theta, you need some consistency, and that is given by this compatibility condition. And once you've defined this, it becomes, you can add and wedge product and take the differential, etc. So again, let me just say, whatever the technical definition may be, there is a notion of tangent space and tangent vectors, and there is a notion of the duals, covectors or differential forms. So we are getting into, differential geometry. It's not geometry in the sense of metric, but in this kind of sense. So then let's look at this notion of chain integral. I have written it in terms of one forms, omega 1, omega 2. But we can also just look at the second equation on this line. If you are given functions f1, f2, fm, you can ignore everything I have talked about up to now. And this definition still makes sense. In fact, this definition is not about diffeologies at all. So if somebody hands us functions f1, f2, fm on an interval, just ordinary functions, we can integrate these functions dt1, dt2, dtm, but you do it in a certain order. First, you integrate f1 up to a certain point, then you take that point and integrate f2, and so on. This is called an iterated integral. You can write, I've written it like this here, but you can write it as literally as a repeated integral. Now, it turns out this is what Chen investigated over many papers in the I guess, starting in the late 50s and ending in the 70s, maybe even 80s. He constructed an enormous theory around these repeated integrals, starting with just ordinary functions. Then you move up to one forms, okay? Then with one forms on a manifold, you do this over a path. And once you've done it on a manifold, he also built it on his space, differential space, but it works also on diffeological spaces. So diffeological spaces are not very good, it seems to me, for doing measured theory and integration in those things. But in doing integration along paths, repeated integrals along paths, these iterated integrals, these things make sense on diffeological spaces. So, and I've mentioned one forms, one can do this with higher order forms also. Chen, what is his huge theory about? He defined these, he proved some wonderful properties, and then he used them to apply to algebraic topology, the homotopy theory, and so on. I mean, he had the whole calculus of these things. And I just want to put this one example here to show, again, you know, I have not presented in detail what this iterated integral is, but just take it as this, that if you are handed one forms like f1x dx, f2x dx, and so on, you can string them along in some particular order, okay? And you get a repeated integral along a path. It's like a line integral. And you do another one, you multiply them. Well, it turns out, and it's not super hard to verify actually, but nonetheless, the result is wonderful, that the product of two such repeated integrals is another repeated integral. And here is this weird operation. It's called shuffle, and somebody once said you should never use a symbol that you cannot pronounce. Well, this is the Russian letter sha for shuffle. Admittedly, this is SHU, but nonetheless. So when this product, even if you're not interested in diffeology or anything, this product itself is kind of funny. If somebody gives you a string of symbols, omega 1 through omega m, whatever they are, and another string of symbols, eta 1 to eta n, this shuffle, what it does is it puts the first m things in between, like two decks of cards, into the other one without changing the order of things. Okay, you have a left deck of cards and a right of deck of cards. You put the lowest one somewhere, then the next upper one into somewhere above that, then the next upper one into something above that, and then you do all such things and you add them up. So this is the shuffle product of two words actually, and this is an interesting product in itself. It's commutative, which is not, at first it seems like, how can it be commutative? But and then, yeah, it's got all kinds of nice algebraic properties you want. So again, if you, diffeology, whatever it may be, just this product. Now, this product was not invented by Chen. It goes back, I looked up, there's a paper by Eilenberg and MacLean on homotopy theory. And they came up with this with some simplices and whatnot. But in this context, it was used by Chen. Okay, so there are many other things that can be done with diffeology. In particular, you can do like a Lie group. All you do is you say, hey, you know, I have a group. If I say that the multiplication operation is smooth, and this thing should be the inverse operation. Then this is just like a Lie group, except for a Lie group, one wants the manifold. In this case, all we want is a diffeology. It's a diffeological group. There are examples, so it's not just an abstract definition, there are examples.
So I don't
Yeah.
know if you defined products of diffeological spaces. Maybe you did. But
No, I didn't. I just said there exist within the
I see.
category of. So to be precise, if you take two diffeological spaces, you just take the Cartesian product as a set, as sets. There is a natural diffeology on it, which makes the projection maps smooth. So just like product topology, actually.
Yeah, that makes sense. Yeah.
And this is the inverse map. Okay, then the last slide, basically, I think, is if you've studied bundle theory by somehow, there is this notion of principal G bundle, where G is a Lie group. And all I have done is, again, this slide is of interest only if you are familiar with principal bundles. And all I have done is I've just taken the definition of principal bundle, and instead of manifold, I've written diffeological space. Okay. And I'm not saying that this is the definition of diffeological principal bundle. Indeed, Dion uses a different definition, which is perhaps not equivalent to this. But this is just to show that you can take the traditional definition from differential geometry and simply replace manifold by diffeological space, and it is meaningful. Then you can do other things, like Dion has been studying differential geometry as in parallel transport and stuff like that. Okay, so the summary is diffeology gives a calculus for spaces, very general spaces. The central idea is that you use smooth functions as a primitive notion, and you call them plots. The category diffeological spaces with smooth maps form a category that has a lot of nice properties. We can define tangent spaces and differential forms. There is an integration theory based on Chen's iterated integrals. And lastly, the theory is rich enough to support counterparts of things in traditional geometry. So these are some papers. All right, well, that is that.
Are there any questions from the audience?
So Dion, I don't know if you want to say any comments or anything.
Yes, Dion, I'm interested in how you are using this theory and how it helps you.
Sure, yeah. So yeah, Amber kind of had some slides at the end about principal bundles and stuff like that. So actually, one of the projects that recently finished, Ambar had suggested to me a long time ago, and it was this paper by Singer. And what he did in this paper is he essentially gave a universal construction where essentially you have a space, something like a manifold, and you have some Lie group kind of floating around, and then there's a homomorphism from the set of loops of that space into that Lie group. And Singer gave this universal construction that, whatever those objects are, you can actually build up a principal G bundle. And this principal bundle comes with this object called a connection. And you can compute something from that connection. It's called the holonomy, but whatever it is, if you compute it, then you recover that group homomorphism. So it's this very beautiful idea in Singer's paper. I think it goes back actually quite a bit before Singer, but at least the idea that I got it from was from Singer's paper in the 1990s. Um, and so it's a good idea, but he admits in his paper that it's a bit of a heuristic idea. And if you look at the construction, he just kind of describes how to do it in words, and then makes a comment that, this is just a heuristic construction. But it seems to be true, there doesn't seem to be a reason why it shouldn't be true. And so what you can do actually is you can kind of modify a lot of his ideas using diffeology. And if you try and put everything into a diffeological framework, there's some theory of diffeological principal bundles and connections. And with enough modification, you can actually formalize all of Singer's constructions and give a correct proof of that result. So that was kind of a fun project and maybe a good example of why diffeology is pretty useful. Oh, I think you are muted, Irfan.
Yeah, so I was curious about how you first learned about diffeology. I'm guessing you probably took a course on differential geometry, but they probably would not tell you about this. So how did you
No,
find
yeah,
this out?
that's right. That's right. So I actually first learned about it through Ambar. It was,
Okay.
I think, my first year PhD. So I'm finishing my third year now, but first year PhD, Ambar I think he just called me randomly one day. I think I was in the middle of
That's
class
good.
and he calls me and kind of said something about diffeology. And I said, "Oh, that sounds interesting."
Mhm.
So he told me a little bit more about it and we looked into it together. And it's a pretty fun topic.
So that question um, about whether one can make precise mathematics out of the idea of Singer, that goes back to maybe around the year 2000. Singer, again, back when I was at LSU, he visited LSU, and I took him from Baton Rouge to New Orleans, and he mentioned a lot of things on that trip. And he mentioned this paper which he had written. And ever since then, it has been on my mind that there must be a way to make those arguments which were heuristic in his presentation precise. So all these years, that question has been on my mind, and then I mentioned it to Dion and to you studied diffeology and you established it within that framework.
Mm.
So this is Matt Insall again. I'm driving, so I can't do video.
That's okay. Yeah.
And so, but this is very interesting. I'd like to learn more about it. So I'll try to be in touch
Sure.
if possible. But I have the following question: have you thought about generalizing it to where the if we call these sort of Euclidean diffeologies, then you could also do something similar with non-Euclidean diffeologies in the sense that you would have, instead of the class of Euclidean spaces as your domain spaces or your open subsets of Euclidean spaces being the domains of your plots, you should be able to use pretty much any topological space.
Yeah, no, that's
Or any category of topological
yeah.
space to construct a different notion of diffeology. And you can also sort of do a kind of or you should be able to do a self-referential kind of thing in a sense where you take as your category of domain spaces and the category of diffeology, the diffeological spaces of one kind or another. And I think you'd get some interesting results there. But I don't know if anybody's done it because I don't know anything about diffeology more than what you told me today and what little I looked at in Wikipedia while you were talking.
No, I haven't heard of this, but it definitely is very intriguing. So it would be, there's a topic called higher gauge theory, which was something I've studied. But this is like higher diffeology. You as you said, you build diffeology, then you use that, you plug that back into the place which was held by the open subsets of Euclidean spaces, and then
a natural question would be: do you get anything new?
Yeah, right.
Do they alter if you start with the Euclidean diffeology spaces the way you've defined them, and then you put those into the domain? Do you just get back Euclidean diffeologies or something that's recognizable as Euclidean diffeologies in a natural way out of that? Because it almost should be naturally the same or almost the same in some sense, just because of composition of maps between sort of composition. I haven't written it all down, of course, but it's
that's
a
a
very
great question.
short idea.
I don't know. I'm not so sure it'll be the same. Maybe it'll be another structure, but maybe. Yeah, anyway, it's a very interesting question. I mean, at some point I was thinking that diffeological spaces are, if I think of a category whose objects are open subsets of Euclidean spaces and morphisms are C-infinity mappings between them, then diffeological spaces are, I don't know what they are, they seem like some kind of an extension of that category. Maybe like cones, I'm not quite sure, it's something like that. But then what you are saying would be like, well, start with the category not of open subsets of Euclidean spaces and C-infinity, but diffeological spaces and C-infinity maps, smooth maps between them.
Right.
And where do you go to that next level? Is it maybe, as you said, perhaps it is, you might just recover the same category, but maybe not. It would be like
or maybe something categorically equivalent or something like that.
Yeah, right, yeah.
I can imagine all kinds of nice variants on the definition in the fundamental definition itself that should be of interest as well.
Yeah.
If you start with Euclidean space with a measure on it, and it might not be Lebesgue measure, it might be a Gaussian measure or something like that, and incorporate the measure into
that's right. If you've opened Pandora's box, it seems.
Yeah, but it might be a very useful one.
Yeah, that's right.
Physics and random structures in mathematics are studied now with exotic category-theoretic variants of probability statistics. Yeah. Thank you very much.
Thank you for that comment.
So I think you said earlier that these structures do not behave well with measures, but then we were just talking about measures.
Yeah, well, that's because I didn't think of this viewpoint.
Well, it would involve an imposition of the collaboration of the measure with the diffeology. That. If you go back to the definition and modify it so you put measures in there, then
Yeah.
of course this will be part of it. But that's a different thing in some sense. But we have variants of differentiability all over the place already. There's weak derivatives
Yes,
in partial differential equations, weak solutions of differential equations where the differential equation doesn't actually hold, but you do an inner product of both sides of the equation. This is a simple version in the introductory courses where that inner product is done with an integral in a function space.
Yes.
And so it sort of defines a new notion of differentiability.
Yes.
Ad hoc at first, and then you can formalize it later.
Yes.
So I have some pedagogical questions that I have had since before the talk. I was telling you before the talk that I struggled a lot in my differential geometry class in my master's in India. And I'm wondering if this perspective helps in the pedagogy of differential geometry in any way. Like if you start from this perspective, are you able to prove some of the basic things in differential geometry more easily or not?
Yeah, that's also an interesting question that I'm often trying to kind of, or not I necessarily, people in the field are trying to justify things by referring to similar things for manifolds, but maybe it could be reversed. Take this as the starting point and make manifolds be defined in, or understand manifolds in relation to this.
There is a really nice example that I actually learned recently where Diffeology can help with proving results in differential geometry. And so one kind of classical result of differential geometry is when you learn de Rham cohomology, right? And one result is if you have maps that are homotopic to each other, then their pullbacks are basically the same in de Rham cohomology, right? So the de Rham cohomology classes are invariant under homotopy. And there's there's a very nice proof of this in differential geometry, but it is something that you have to learn if you're learning differential geometry for the first time. In Diffeology, what you can actually do is you can take a shortcut into the path space. And so it makes this proof a lot shorter, and I find a lot more natural too. So the classical proof of that is you have this like chain homotopy operator, right? It does this like weird thing with the exterior derivative. You have something like that in Diffeology too, except it takes in forms on path space, and it makes the proof a lot shorter and proves that result for manifolds, but also for diffeological spaces too. So that's an example that I learned pretty recently, and it's one of my favorite
I think the
examples.
spirit of Chen sparkles. So, he moved a lot of things from the manifold to the path space. And in fact, that is why he was interested in in his differential spaces.
Yeah,
So
yeah.
we have a raised hand.
Irfan told me that your talk was going to be very technical, but that did not deter me from zooming in with you all. I've been attending the discussions for over a year now. The highest level of math I took was Algebra 2 in high school. I have a very fascinating interest in crossover applications of broad mathematical concepts to everyday situations, especially political situations, conflict, injustice, and the like. Because we're all living in a world with multiple objects, people, institutions, take the whole gamut, and a complex set of relationships amongst and between us. And the challenge managing society is how do you deal with such complexity in which the individual components really represent worlds within themselves with a set of rules and laws about how they operate, and how does all of this interact? Well, I'm trying to give you some introduction to my query, Ambar, and it is triggered by the news announcement that open source AI had gone rogue, meaning that it had departed from its design purpose and the architecture of an artificial intelligence space is supposed to allow it to go through various transformations or changes. It does its job, it thinks, but yet it should maintain its original intent and form. So here's a situation where if I'm following in my naive, if not vulgar, understanding of what you're talking about, that it did not maintain, it lost its topology. When an AI system goes rogue, it loses its topology. And when the designers set it up and when they are thinking about safety measures, the way I look at it in my own layperson way is that it is supposed to maintain its original design and intent. And when it does not do that, Houston, we have a problem, as they say in rocket science.
Yes.
If I'm picking up nuances and intuitions about all of what you're conveying about Diffeology, can you say something about Diffeology in relationship to the phenomenon of AI systems going rogue? And say something about my everyday understanding / math reach for understanding that the way of looking at this is that the AI system has somehow lost its topology.
So I have, of course, never thought of this in this direction. It's a novel idea to me. I mean, I do know that category theory has some unexpected applications, or at least it can provide a language to understand things that were not, for which it was not invented. And I don't know, it could be that there is some relevance, some potential value in maybe not so much the diffeology, but the more abstract structure, category-theoretic structure of it could be useful beyond the specific mathematical application I have in mind.
Okay, so I wasn't too far off. Thank you.
So with AI, you know, we are every day brings in new news. May I ask your background? Is that a real background, or is it a?
Oh, that is a real background.
Yes,
I'll just
like it.
to the screen.
Mm-hmm.
I live outside Philadelphia. The artist, Patricia Hillman, I've been collecting her work for over 2 decades.
Wow.
And she brings the head and the heart into harmony in her work. So you always see gears and technical devices.
Yeah, I see the head and the heart. What you're saying, yeah.
I think what we're doing here in our compassionate math discussions is definitely relates to that. And what has been a discovery process for me is the inherent passion within mathematical thinking. I mean, the language and the symbols that you use to express the truths that you see are arcane, but in between the sentences and in your discourse, there's so much. You can hear the inventiveness, the curiosity, and the depth and levels of thinking about what you're thinking about. It's really quite amazing. These are thought structures and networks and complexes of extraordinary depth. And if you try to visualize it, you then, at least for me, my next step is to connect that with your feelings, because you're sentient beings. You're also highly cognitive, but you're feeling. And that must be some correlation in this journey of thought to a course of emotions that you have. And so there's a softening and expansion of your heart that is parallel to what would have to be the expansion of your minds and your capacity to think and to embrace complex understandings. This whole process of engagement and living your life vocationally and avocationally creates a vision in my mind of a community of people who are on a trajectory of human evolution and consciousness of human being that equips you to deal with complexity in our world and the problems that extreme complexity in human relationships pose for all of the caretakers of our crumbling civilization. So you, aside and apart from your vocation as mathematicians, I see you as a community of thinkers, as a great source of hope for insights and breakthroughs in terms of how we can look at the devastating problems that are perplexing our world today. Because, long story short, one subset of the problem that our leaders are facing is their inability to deal with not only cognitive complexity, but what I was saying about the mathematicians' evolution from their thinking advancement is that connected to that is a heart and a passionate, emotive evolution that brings head and heart together, that will equip you to sustain yourself through a very arduous process of trying to deal with the complexity of human life and the political problems that that complexity brings to us. Because the content of what we're dealing with is one thing, but what your mentality provides is an ability to look at the complex issues of social politics, culture, and conflict in a more abstract way. And what would be a wonderful witness to our leaders who are failing would be to see you sustain yourself emotionally and psychologically as you deal with complexity. Because I don't think our leaders have the ability to bring their head and their heart together in dealing with these matters. But I think mathematicians have more possibilities in this area.
Thank you. So, Irfan,
Yes.
I have to sign off. Again, thank you for the opportunity, and thank you to all of you who are here, who listened, who commented, and those who listened. Thank you.
And thank you.
Thank you for a great talk.
Bye.
All right. Bye. Okay, I finished that stream. If anyone wants to stay, you can stay for a while.